Yes, ma'am.
Okay.
Hello.
So now after this, we are having detecting the electrons. How do we detect the electrons? Okay. Let's start with that. So basically, we cannot see electrons directly. We need a detector to find out that where are they going and how are they behaving. Okay. So when the electron collision happens, it actually gives out the energy. Okay. Which we actually, from where we can make a assurance that the electron is moving from here. Okay. So the electrons basically gets collide with the atoms, that is the vacant atoms. Done. Now when the
Yes.
atomic electrons go back down to a lower energy level, they give out light, which is known as phosphorescence light. I'm saying when the electron go back to lower energy level, they give phosphorescence light. Okay, fine. And it can be used to see where the electrons are landing. Done?
Yes, ma'am.
Now basically your zinc sulfide is one such element, okay, which is used to coat the glass screens, so that the light is emitted where the electron collide with the screen. Okay,
Yes, ma'am.
fine. Now this is how older types of 3V screens also work, and we can identify that where the electrons are going. Okay. Now after this, one more topic is there, which is known as electron diffraction. So basically, if a beam of electron is passed through a thin film of graphite, okay, then what happens is an interesting spectrum is observed when they are hitting a screen which is phosphor in nature, which is carrying phosphor. Okay. And the pattern looks like very similar to the diffraction pattern. Here, the pattern is similar to diffraction pattern. Done?
Yes,
So
ma'am.
now after this, it causes the light when the light is diffracted by a very small circular aperture. Okay, fine. That is from here, if a very small circular aperture is there and it's going out from here. Okay. Now assuming this to be true, we can calculate the wavelength of the wave and which got diffracted. So here comes the topic of de Broglie wavelength. Now what is de Broglie wavelength? Basically de Broglie was a scientist. In 1924, he had proposed a theory which is known as all matter has a wave-like nature. Done. And it is equivalent to the wavelength of h over p, where p is the momentum of particle. Okay.
Yes,
So
ma'am.
using this equation, we can also calculate the wavelength of electron that is accelerating through a potential of 50 volt. Done.
Yes, ma'am.
Done. So what is the kinetic energy obtained by the electrons are 50 electron volt, which is nothing but 10 into 10 raised to minus 18 joules. Done. Now it is also having the formula half mv square. So that will be saying that V equals to 2 into Ek over M. So when I put all the values over here, that is 2 into 8 into 10 to the power of minus 18 over mass of any electron is 9.1 into 10 raised to minus 31. So I will get the answer 4.2 into 10 raised to 6 meter per second, with the help of which even I can find out the momentum, which is nothing but 9.1 into 10 raised to minus 31 into 4.2 into 10 raised to 6, which will give you 3.8 into 10 raised to minus 24 Newton second momentum. Then hence we can find out the wavelength, which is h over mv. So it will be 1.7 into 10 raised to minus 10 meters. Done. So basically the wavelength that we are using here is used to see the diffraction pattern of the light through the diffraction grating and to calculate the angle of very first maxima of the diffraction pattern. So we are aware that n lambda equals to 2d sine theta, or even we can write it as sine theta equals to lambda over d, because here n equals to 1.
Yes, ma'am.
Okay. And
Yes,
only first maxima we are using, so 2 will not come. Done. So from here we can say that the diameter is the atomic spacing over here, which is nothing but 2 into 10 to the power of minus 10. And the theta is calculated as 60 degree. Okay. So basically it is nothing but the distance between the fringe or the atomic spacing also we say. Done. Okay. Do you want to know anything out of it?
No,
Facing.
once again, no, ma'am. I'm just copying the P.
Okay, done. Write it.
Yes, ma'am. Ma'am.
Are you done?
Yes, ma'am.
Shall I scroll it down?
Yes, ma'am. Yes, this part. Once again. Yes, ma'am. Ma'am?
Yeah.
Yes, ma'am.
Are you done with this?
Yes, ma'am.
Okay. So now let's have a look at the probability waves, that how it will be looking. So it basically looks like interference wave pattern. Okay. Let me show you that part also. Check. So it will look something like this. Okay.
Yes, ma'am.
Fine. Whatever theoretical study is there, please do it. Interference already I had explained in the interference chapter. Okay. So related to this, do the study. Next is Crompton effect. Let's have a look over this. What is Crompton effect? So basically, a photon is not a real particle, we are aware, right? It is
Yes,
just an energy packet which travels like a wave. Okay. And it is a packet of wave. Done. Now, if this was a particle, surely it would bounce off other particles to conserve the momentum. Done. Then how can the photon, which has no mass, will have some momentum? That is the question which is occurring over here. Okay, because if some mass is there, it should have some energy, hence some momentum is there. But photon have no mass. So how does it show the momentum? So photons do have the momentum and they do collide with the electrons. Okay. But when this happens, the kinetic energy and the momentum gets conserved. Okay, this was given by a scientist that is named as Arthur Crump. Done. So this effect is named after him. Okay, what does he see? That the X-rays get scattered by the carbon target. Done. What he's as given the in Crompton effect, that photons also show momentum because they, when they collide with the electrons, they conserve their momentum and do collide with the electrons. Okay. Now the kinetic energy and the momentum here are conserved basically. Done.
Can you repeat, like you were saying, but then for a while, like your voice stopped, and then it again came back.
Okay, now listen very carefully. I'm saying that photon is not a real particle. Unlike electrons, it is a packet of waves. Okay.
Yes, ma'am.
And if it is a particle, it will surely bounce off other particles and it will conserve momentum. Okay. But
Yes,
photon is not a particle, hence how it could have any mass or momentum? That is the question. So it is described by Crompton. What does he told? That photons also have momentum. They also collide with the electrons. But when this happens, their kinetic energy and momentum gets conserved. Okay. How
yes,
does
ma'am.
it get conserved? That the X-ray scattered by any carbon target, suppose if we take, and the wavelength of that scattered photon if changes, so that the effect cannot be explained by diffraction. Okay.
Yes,
I'm
ma'am.
saying X-rays got scattered by the carbon target. Here I am having a carbon target. X-rays are scattering over it. Okay. Now, the effect cannot be explained by diffraction pattern, but the greater the extent of the scattering of the wavelength, the higher the wavelength becomes for the X-rays. Understood?
Yes, ma'am.
Means if scattering is high, the wavelength will also become high. Okay, now let us apply the conservation of energy and momentum rule over here in between the photons and the electrons, and let's calculate the energy, momentum of these particles. Okay, so from relativistic mechanism, we can show that energy of a particle is given by E square equals to m square c power 4 or p square c square. Done?
Yes, ma'am.
If suppose I consider that the mass of photon is 0, therefore this whole term will become 0. Correct?
Yes, ma'am.
Therefore my E will become equal to Pc. Hence my P is nothing but E over C. I am aware that my E is equal to HF and that is equals to HC over lambda. Let's put this in this value. So my P will be HC over lambda over C. C will get cancelled out and I'm remaining with P equals to H lambda. So here it means that the change in momentum will result in the change of wavelength also. Okay. And if we consider, suppose, get this diagram now. If we consider this diagram where a red ball is having hitting the blue ball, then the change in momentum of the red ball is seen. Okay. And it depends upon the angle of the deflection. Here it is got deflected at this angle. Here it got deflected at this angle. Okay. So if the red ball just hits the edge of the blue ball, the momentum will hardly change, but a red on collision, head on collision will cause a larger change. Okay.
Yes, ma'am.
So it will be same as the photons. Done?
Yes, ma'am.
So bigger the angle of deviation, the greater is the change in momentum. Done?
Yes, ma'am.
So this equation can also be related with the wavelength again. What is the wavelength of the final position minus the initial position? That is the delta change of the wavelength will be h over mc. 1 minus cos theta. So this is the formula for determining the wavelength. Whose wavelength? Let me show you that. Crompton scattering, you can see here it is photon is moving with initial wavelength. It got collided with electron. So here it gone with the recoiled electron is gone there, and the photon is gone there. So it had got deviated from the horizontal at a phi angle, whereas this had got deflected at some theta angle. So this is my scattering photon, and this will be my recoiling electron. Now let's have a look over here. This is blue in color, this is red in color. So basically it implies us that blue has a very, very low frequency, but red has a very, very high frequency. Understood? So here the wavelength is high.
Yes, ma'am.
For red color, the wavelength is high, sorry, right?
Yes, ma'am.
Okay. Now let's solve one question dependent upon this. Okay. And if you want, you can even do, but you need to be very fast.
Okay, ma'am.
Calculate the wavelength of 0.002 nanometers photons, which is scattered at 90-degree angle. So your cos theta is cos 90 is, so cos theta will become cos 90. H value is fixed, which is 6.63 10 raised to minus 34. Mass of electron is fixed, 9.1 10 raised to minus 31. C value is fixed, 3 into 10 to the power of 8. Please solve.
Yes, ma'am.
Are you done?
One second, one second.
Kindly be quick.
Yes, ma'am.
Okay. So moving ahead, we have the next chapter, and that is radioactive decay. Let's start with that. So in radioactive decay, our very first pointer is
it 4.43, ma'am? That one. The
previous one.
yes.
0.0044 nanometer.
4.443.
Yeah, you are correct, but somewhere these things are missing. Check.
Okay.
Okay.
Yes, ma'am.
So here the very first topic is the nuclear forces. Basically, nuclear forces are of two types. Very first one is weak nuclear force, then strong nuclear force. Okay. So strong nuclear forces is having, let's talk about this one by one. Strong nuclear forces are of very short range. Okay.
Yes, ma'am.
It only acts up to the distance of 10 raised to minus 15 meters. Hence, it is only found in nucleus, in between proton and proton and neutron. Done?
Yes, ma'am.
Yeah, I am here. Don't worry.
Yes.
Okay. So what I was explaining, that strong nuclear forces are there, which is existing in between the nucleons only in the nucleus, right? So a
Yes.
combination of proton and neutron, a combination of neutron and neutron, a combination of proton and proton basically acts on it. Okay. Now let's have a look over the graph of it. That is force between the nucleons 10 raised to minus 4 Newton it is. Attractive and repulsive forces are shown. Okay. So Coulomb repulsion between two protons is here. And equilibrium position of the proton, that is the sum of two forces, is always 0, which is shown with a blue dotted line, a straight line. Here is the nucleon separation is shown on this x-axis. On y-axis, forces between the nucleus is shown. And the red color will show you the strong nuclear force between two nucleons. Okay. So first it is very, very, very repulsive. Now after some time it becomes the negative energy and hence it starts attracting. Okay.
Yes, ma'am.
Okay. So now after this we are having the strong nuclear force does not exist in the nuclei of more than one proton. Okay. And would not exist either. Okay. So the electric force that repels protons would exceed the gravitational force attracting them. Okay. Understood or not?
Yes, ma'am.
Let's have a look over this again. Check this. So the neutron number as increases and as the proton number increases, you can see till here till 20. The line of the line is linear. That is the number of neutrons and the protons are equal. Okay.
Yes, ma'am.
But line of stability is going little bit up. Okay, which is not coinciding with black line. Hence till here only till 20 number of the protons and neutrons, that is the atomic number 20 only, you can see a strong nuclear forces inside the nucleus. Okay.
Yes, ma'am.
Any doubt?
No, ma'am.
Fine. So now after this, as per the graph, you can see the strong nuclear forces are very short range, hence it does not exist and act fully across the large nuclei. Okay. However, the repulsive electric force does. Okay. For this reason only, the nuclei with a larger number of the nucleons require very high ratio of neutrons and protons, so that in comparison to the small nuclei. Okay.
Yes, ma'am.
So that they can reach the stability stage. So the neutrons provide very equal amount of strong nuclear forces and provide the additional spacing between the protons. Done. Now the next topic is binding energy. So let's talk about the binding energy now. So what do we understand by binding energy? Binding energy of the nucleus is defined as the amount of energy required to separate the nucleus into its constituent protons and neutrons. Understood?
Yes, ma'am.
The binding energy of a nucleus is defined as the amount of energy required to separate a nucleus into its constituent protons and neutrons. Please note it down.
Yes, ma'am. Two. Yes, ma'am.
Are you done?
Yes, ma'am.
Show me one example as per the given definition. How will you show the binding energy here?
The
The binding energy for any thing.
helium.
Shall I give you one question or like that? What are you saying?
No, ma'am. Like helium will be
Hmm.
not helium.
You can show me. Show the example of helium. It will be fine.
I think it is the. It starts with U. Uranium, and it it breaks down into this and I think this one element and an alpha particle.
Your voice is very low. It's not audible.
Hello, ma'am. Can you hear me?
Yeah. It's. I'm saying you are saying that is correct, but it's not. It's very slow. That is what I'm saying. Need to be little louder.
It is like it's like a equation, ma'am. Like uranium will be equal to mass of I don't remember the equation, ma'am.
Okay. Fine, no issue, Akshita. Let's move ahead. Almost I got it, what you were saying. Fine. But let's have a look now at
Yes,
the
ma'am.
picture that I'm showing you. Okay. Sorry. Check. So there is a blue ball which is bouncing out. Okay. And when it takes the energy, it will go jump. It will jump in a very high height. Okay. So here also, if suppose here from here 1 electron, 1 proton is coming, from here 2 electron, 1 proton is coming. Sorry, these are neutrons, green one. Okay. And they actually collide. One neutron comes out of it and the 2 and 2 gets emitted. Done?
Yes, ma'am.
Okay. Now, what is the conversion of AMU into MeV? Basically, I'm talking about energies. Okay. So, what is the conversion from one atomic mass unit to MeV, which is nothing but 931.4. Okay. But still, like, if it has been asked in exam, you should be aware of how it has been derived. So, what happens is atomic mass unit is basically defined as what? 1/12 of the atom of carbon-12 atom. You are aware, right?
Yes, ma'am.
One atomic mass unit defined as the 1/12 of the atom of carbon-12 atom. Okay, and that is how much? 1.6 into 10 raised to minus 27 kgs. Okay.
Yes, ma'am.
Formula is E equals to mc square. So this is the energy. Done?
Yes, ma'am.
Sorry, this is the mass. My bad. This is the mass. This
Yes,
one
ma'am.
is mass. This is C square. 3 into 10 to the power of 8. And this is what the joules in energy we got. Now, with this, we will divide 1.6 into 10 raised to minus 19. Why? Because E equals to mc square. And we are aware that we had calculated E. Okay. When we convert the electron volt into joules, the formula is 1 EV is equal to 1.6 into 10 raised to minus 19 joules. Okay. Now I have to convert it into MEV. So what will happen? I will multiply this with 6, right? Because this is mega electron volt. Can you see here?
Yes, ma'am.
Any doubts?
No, ma'am.
Sure.
Yes, ma'am.
So he had just converted the
EV to joule.
EV to MEV, and that is how we got 931.4. So basically you just have to write that 1 plus AU is given as 931.4 MeV of energy. Understood?
Yes, ma'am.
Any doubts?
No, ma'am.
Okay, good. So this is all about this. Now let's calculate the binding energy. Okay, I'll show you that thing also. So you just have a look over this. Let's calculate the amount of energy required. For this given table. Check. Can you see this table? Hydrogen is having AU of 1.0, neutron is having this much, and iron is having this much. So let's calculate this part.
Yes, ma'am.
At how much binding energy it does have. Fine. So check. Basically, table contain atomic masses rather than the nuclear masses. So this is the mass of the neutral atom. Okay. And it includes the Z electrons. Okay.
Yes, ma'am.
A is the mass number. Z is the atomic number. So Z could be number of protons, could be number of electrons. Understood?
Yes,
For
ma'am.
an element, we write it like this. Done? So here the atomic mass is used to calculate the mass defect. We will calculate the mass defect, okay? To make
Yes,
sure that the electron mass cancel out each other. Okay. Now let's see how they are calculating it. So basically energy is nothing but mc square. Okay. Where m is the mass difference between the iron nucleus and the nucleons. Correct? This is
Yes,
what
ma'am.
the binding energy suggests.
Yes,
So we
ma'am.
will find out first the mass of the whole nucleus. Then after that one by one nucleons. So let's calculate it. So mass of parts. So mass of 26 proton and mass of 28 neutron, that is in the nucleon, minus the mass of the iron nucleus. Let's have a look over this. Any doubts that you are facing?
No, ma'am. I think I'm kind of familiar with this.
Yeah, exactly. That's why I'm actually repeating it a very fast pace. Done. So
Yes.
5426 is here at iron. Okay, written very clearly. Hence, 54 minus 26, that means it is having 28 number of neutrons. So 26 multiply mass of hydrogen atom, 26 multiply mass of electrons, plus 28 mass of neutrons. Any doubt?
No, ma'am.
Sure.
Yes, ma'am.
Okay. So now after this, we are having the numbers 26 into mass of hydrogen atom plus 28 mass of neutron minus mass of iron atom. So what is 26 into mass of hydrogen? 1.0. 28 into mass of neutron? 1.0. Mass of iron 54 atom. So obviously as it is 0 only, so we will write it 53.93. Done?
Yes, ma'am.
Okay. See, it is written here. Okay, in the table. When we have sorted it, simplified it, we got the answer 0.50, which is equivalent to 931.5 multiply. So 471 MeV of energy. Any doubts?
No, ma'am.
You want to ask anything out of it?
No, ma'am.
Okay. So now let's do the next topic, that is binding energy per nucleon. Okay. So till iron, the nucleus are stable because smaller nuclei are only stable in nature. We are aware of it, right? After that, binding energy per nucleon decreases and hence the atoms becomes unstable in nature. And the graph obtained is something like this. Nucleon number from 0 to 1, 2, 3, 4, 5, 6 till 200. Here the binding energy per nucleon in MeV is given. So for these atoms, it is almost fixed. The last atom is found to be iron, where it is fixed. After that, it drops. Okay?
Yes, ma'am.
Very good. Now, so large nuclei generally have a very high binding energy than the smaller nuclei. Okay? Since they have more particles in it, hence they will bear more kinetic energy. Okay, Akshita?
Yes, ma'am.
Akshita?
Hello, ma'am.
Yeah, am I audible?
Yes, ma'am.
Okay. So, to compare one nucleus with the another nucleus, it is better to calculate the binding energy per nucleon. So, you can see the graph. Anything you want to ask?
The other one undergoes, like the larger one undergoes fission and the smaller one undergoes fusion, ma'am. Like from the graph.
Okay, which one goes under which reaction, that we will see. The smaller nuclei basically go into fusion reactions and the larger nuclei undergoes fission reaction. Okay? Fine. So let's calculate the binding energy per nucleon. Let's say I am calculating for iron only. So it will be nothing but 54 multiply, not multiply, but its total energy. What is its total energy? 471.5. So how much energy per nucleon is bearing? Nearly 8.7 MeV. Okay. So that you can check from here also. It is nucleon number is 54 and from here you can check it is nearly 8.7. Done? Any doubts?
No, ma'am.
Okay. So this is how we calculate the per nucleon energy. Now after this our topic is radioactive decay. Let's do radioactive decay. What happens in radioactive decay? It's a completely random and spontaneous process. It can happen anytime. Okay. So what happens is it emits three types of rays. Very first one is alpha ray, which is comparable to the helium nucleus, that is 4 and 2. Done. And it is basically written as alpha 4 2. And it is having positive behavior. It behaves like a positive nuclei.
Yes, ma'am.
Pairs a positive behavior. Done. Now after this, we are having beta plus decay. So in beta plus decay, you get beta plus 1 and 0. So mass number does not change. Okay. Only the atomic number changes. So it is also behaving like a positive nuclei. In beta negative decay, it comes out with beta decay minus 1, 0 and it behaves like a negative particle. The difference is in beta plus, your proton number will convert into neutron number inside the nucleus and it will release the beta plus decay. Whereas inside the nucleus, the neutron gets converted into proton and it releases the beta minus decay. Any doubts?
No, ma'am.
Okay. So the last one is your gamma ray. Gamma ray is a just packet of energy. So it is released like a wave. Gamma. Okay. Done?
Yes, ma'am.
So basically a neutron converts into proton and hence beta minus is released that you have to take care of. Whereas when proton converts into neutron, it releases the positive beta decay ray. Okay.
Yes, ma'am.
Let's do the next. And that is detecting radiation. Okay. So how do we detect these rays? Now the question comes is this. So with the help of Geiger-Müller counter, let me show you that. Check this. Whenever
Yes.
any particular alpha beta enters into this cylinder, it ionizes with the rod when it comes in contact with the rod because rod is releasing continuously the electrons, free electrons. When it comes in contact of it, basically it creates a collision and it creates a spark. Here, if I connect a reader, who is reading these counts that how many sparks have got happened. So it will calculate the number of radiations. Done. Now if
Yes.
it is connected to a ammeter so that it can show that how much current is passing through. So here if the amount of current increases of fluctuation, that means some spark have got happened over here and this is connected to battery. Any doubts?
No, ma'am.
Okay, now let's calculate that how does the alpha, beta, gamma ray actually show their collision, or I should say their penetrating power. Okay, so alpha ray is a very short range, it can travel and it gets absorbed very easily in papers also, it travels a very smaller distance. Beta decay is absorbed in the metal sheets like aluminium, but it can travel a little longer distance. Gamma ray can travel a very longer distance. It barely gets trapped in any paper or aluminium sheet. It does not get, and hence it get block of lead if it is coming in between. So metal blocks, it gets absorbed in that. Understood?
Yes, ma'am.
Okay, now let me give you the exact data also for this. Okay. So here is the data for this that says that alpha particles are absorbed very easily. They can travel about 5 centimeter in air before they get absorbed. Okay. And they cannot penetrate the skin. Beta particle fairly easily pass through the paper and the air, but they get absorbed in few millimeter of sheets. Gamma radiations are most penetrating. They take several centimeter of the dense metal like lead, so that or concrete to get absorbed. Okay, understood?
Yes, ma'am.
Okay, now let me show you the path track of alpha, beta and gamma. So a bubble chamber is created. Okay. Okay. Now, bubble chamber is created for what purpose? It's just an alternative method to detect the radioactive particle. Okay. That is in the cloud chamber. It contains basically a vapor of droplets of liquid and the ionizing particles. Okay. Then the droplets of these visible particles or lines are showing that the path of the particle is passing from where. Okay.
Yes, ma'am.
So the vapor trail behind the airplane like that only, the bubble chamber is similar to that only. Okay, let me show you that diagram. So it is just an alternating method. Check. Bubble chamber. So it's an alternating method. So it contains two things. What are those? Vapor of water droplets and ionizing particles. Okay. So whenever
Yes.
the ionizing particles like alpha, beta, gamma, any one of them passes through it, then it creates a spark and it gives a track of that particle. Okay. So this bubble chamber gives the count of that particle. Understood?
Yes, ma'am.
Any doubts?
No, ma'am.
Okay. So we will stop here only and we will continue tomorrow. Okay.
Okay, ma'am.
Fine, Akshita?
Yes, ma'am.
Okay. Bye-bye. Have a nice day.
Bye, ma'am. Thank you, ma'am.
Yeah.